In this lecture, we'll see how computer arithmetic is performed. But first thing first, let us see how numbers are represented in computer. We'll first talk about integers. Let us revisit the decimal number system. Integer. When we talk about the decimal number system, in the case of a decimal number system, the radix is 10. By radix we mean there are 10 digits. The digits are 0 to 9. When we represent a number, say 204, this essentially is a positional number system. By that, every digit position has a weight. The zeroth, we call the 0th digit position has a weight of 10 to the power 0. The first digit position has a weight of 10 to the power 1, and this has a weight of 10 to the power 2. And this number therefore is 2 into 10 to the power 2 plus 0 into 10 to the power 1 plus 4 into 10 to the power 0. Now, in the case of a binary number system, the radix that we use is 2. Therefore, the digits, we call it bits in the case of a binary number system, is 0 and 1. This is also a positional number system, which means that if we say there is a number 101, then the first position has weight of 2 to the power 0, the second has a weight of 2 to the power 1, and third has a weight of 2 to the power 2, which means this number, when we represent 101, is 1 into 2 to the power 2 plus 0 into 2 to the power 1 plus 1 into 2 to the power 0, which is 4 plus 0 plus 1. This is equal to 5. Now, when you're talking this way, either here, in the case of a decimal number, or here, in the case of a binary number whose radix is 2, we are talking essentially of an unsigned number. The sign has not been taken into consideration. Now, when you talk about a signed number, in the case of a decimal number, if we say that it's a positive number, we say it is plus. When we talk that it's a negative number, we say it is a minus. Say minus 535 is a negative number represented by a minus sign at the beginning. In the case of a binary number, the positive number therefore can be represented with a sign bit. We say 0 in the means a positive number. If we say 1, then we call it a negative number. Now, when we represent it this way, that means we have the magnitude of a number, say 101, which is 5, preceded by 0 to say that it is positive, then and say another number, once more say 101, which is 5, preceded by a 1 to represent that this is a negative number. We call it a sign magnitude representation. This is our sign bit and this is the magnitude bit. Say for example, we are talking about a 4-bit number. In the case of a 4-bit number, we have, if I write 0, 1, 1, this is, and a 0 here, the most significant bit 0, this is our plus 3. And if I write say 1, 0, 1, 1, the most significant bit being 1, we call it minus 3. Just to have the representation clear, we'll take this form that if we have an n-bit number, this is a convention. Then this one is a 0th bit, this is a first bit, this is a second bit, this is a third bit, and so on. This is n minus second bit, this is n minus first bit, and these are the n bits. For example, if we have a number, say 1, 0, 1, say 0, and so on, 0, and if this bit, the n minus 1th bit is 0, then this is a positive number. We call this to be most significant bit. This we call least significant bit. Our convention is that if this is the most significant bit or n minus 1th bit is 0, then it is positive. If the n minus 1th bit is 1, then this is a negative number. This is our 0th bit. Let me repeat. This is our n minus 1th bit in our n bit representation. Now, when we talk about such sign magnitude representation, there are certain problems with arithmetic. Let us see what are the problems with arithmetic when we have the sign magnitude representation. Let us take the case that we have minus 5 represented by 1, 1, 0, 1, and we have plus 3 represented by 0, 0, 1, 1, and operation that is we wish to perform is plus. In that case, you see, to actually have the result, the actual operation that has to be done is that we'll have to subtract 3 from 5 and then declare the result to be negative. That means you will have the result as 0, 1, 0 and declare the result as negative, which is your minus 2. So to have the result, we'll have to consider the magnitude of the two operands, the sign of the two operands, and the actual operation to ultimately decide, and operation desired to ultimately decide which will be the actual operation and what will be the sign. Okay, let us take another example. Say we have plus 2 represented as 0, 0, 1, 0 in our sign magnitude form. We want to subtract minus 3 from it. So minus 3 will be therefore 1, 0, 1, 1. Now the actual operation therefore that has to be performed is addition, and we have and the result has to be declared to be positive. Okay. Let us take a third example, say plus 5, which is our 0, 1, 0, 1, and minus 5, which is 1, 1, 0, 1, and the operation that we desire to perform is plus. We have to subtract the magnitude of operand 2 from operand 1, and the result is 0. The result is 0, okay, but what 0? Is it a positive 0 or a negative 0? So you see that the sign magnitude have this problem, that one is that there is not an unique 0, there can be a positive 0 and a negative 0. This is one. And another problem is that to finally get the result, you will have to see the magnitudes of the two operands, sign of the two operands, and the desired operation to determine what is the actual operation and what will be the sign of it. So it is rarely that sign magnitude representation is used in the case of a computer. What we actually use is a 2's complement representation to have positive and negative integers represented inside computer. Let us see what we have in the case of a positive 2's complement representation. Now, in the case of a 2's complement representation, a positive number, say 101, which is 5, if you want to represent that it is plus 5, we represent the same way, which is 0 at the beginning of it. But if we want to represent minus 5, okay, what we do is this, we take 1 0 0 0, this being a 4-bit representation, okay, take 0 1 0 1 and subtract it. If we, in that case, what we get is 1 1 0 1 and this is 0, okay, which means that we have 1 subtract plus 5, representation of plus 5 from 2 to the power 4, okay, subtract this to get a representation of bits which we say that it is our minus 5, okay. Therefore, to get minus 5, we take plus 5, subtract it from 2 to the power 4, that is our minus 5. Now, in the case of a general representation, therefore, if we have a number a and we want to get minus a in an n-bit representation, we take 2 to the power n minus a to represent minus a. This is called 2's complement representation. Now let us see, when we tell that, let's take another example, okay. Say we have, say 0 0 1 1, this is our plus 3. We want to represent minus 3, we take 1, then 0 0 0 0, subtract it from there, okay, then we get 1 0 1, this is 1 and this is 0 and this 0 is neglected, and this is our representation of minus 3. Now, if we examine this, we see that the sign bit is represented by 1 to say that it's negative, and this total thing represents minus 3 in 2's complement form, okay. Now, say this 1 0 0 4 zeros, which is equal to 2 to the power 4, can be represented as 1 1 1 1, which is 2 to the power 4 minus 1, and then if we add 1 to it, then we get 1 0 0 0 0, which is our 2 to the power 4. Now, when we want to get a negative number represented as 2 to the power 4 minus a, that means when we want to have 2 to the power 4 minus a, what we can do is this, we take 2 to the power 4 minus 1 minus a and then add 1 to it. That means we first find this one and then add 1 to it. This has an advantage. Say, once more we want to find minus 3, then let us see that we take 0 0 1 1, which is our plus 3, take 2 to the power 4 minus a, which is 1 1 1 1, subtract it, this is our 2 to the power 4 minus 1, subtract it, we get 0 here, 0 here, 1 here, 1 here, which means each bit we complement, okay. This we call 1's complement, and then add 1 to it, we get 1, 1, 0, 1, which is our minus 3 in 2's complement form, which means that we first compute this and then add 1. Computing this is nothing but complement each bit. This bit is 0, this bit has been complemented to 0, this is to 1 and this is to 1, and then add 1 to it. That way, getting 2's complement is much easier computationally. Now, if we represent it this way, and if we take a 4-bit number system for ease of representation within this limited space, you see that these are the numbers that we can represent. This is our 0, and this is a unique 0 so far as the number representation in 2's complement form is concerned. On one side of it, these are all the positive numbers with zeros the most significant bit, that means n minus 1th bit, and this is all negative numbers, that is we can represent in 4 bits in 2's complement representation with 1s in the most significant bit to represent that this is a negative number. And you see that we can go in the maximum side up to minus 8 in a case of a 4-bit representation, which is the minimum number that you can represent, and this is equal to minus 2 to the power n minus 1. In this case, n is equal to 4, therefore this is minus 8. On this side, we can go up to the maximum of 2 to the power n minus 1 minus 1, which is 7 here in the case of a 4-bit representation. Now, one problem in 2's complement form gets solved, which we had in sign magnitude, is that we have an unique 0 now. Now, what are the other advantages? Let us try to see. Say we have a number which is plus 4, and plus 4 is our 0, 1, 0, 0, and say we have minus 2 here, and minus 2's representation is 1, 1, 1, 0, okay. And the operation that we desire is that we want to add. Now, you see, instead of looking at anything, you simply can add these two representation to get the result. For example, you simply add 0, 1, 0, and this will be 0. There will be a carry out of this bit, okay, which we ignore, and this you can see is a representation of plus 2 in our 2's complement representation. Therefore, when we do an operation, addition operation, we do not have to bother about what is the signs of these two operands. You simply add, and whatever is the result the representation of the result in the 2's complement form. Now, let us see another example where we have plus 4 represented by 0, 1, 0, 0, and a minus 2, okay, say minus 2 once more is 1, 1, 1, 0, and you're doing a, say, want to do a subtraction, right? In this case, when you want to do a subtraction, what we do is this, that you convert minus 2 into its 2's complement representation, since operation desired is minus. Now, convert this into 2's complement representation is easy, as I said. Find the 1's complement representation by complementing each bit and then add 1 to it. And in that case, what we get here is this 0, 0, 1, 0, which turns out to be plus 2. And then what you do is that instead of this negative operation, you simply do an addition operation. In that case, what you get is 0, 1, 1, 0, which is your plus 6. Let's repeat. If the operation is positive, then you simply add the two representation to get the final result in 2's complement form. If the operation is negative, then you simply find the 2's complement representation of the original number, and instead of subtraction, you simply do an addition. Therefore, what you need to add and subtract is not an adder subtractor, but simply an adder with a 2's complement, with a provision of finding the 2's complement representation of a number. Okay, if we have it, in that case, subtraction is no more necessary. Only addition is necessary to do addition and subtraction both. Now, let's see an arrangement like this. What arrangement we can have? So we have simply an adder. This is our adder subtractor unit. This is our operand 1. This is operand 2, where we have a subunit which determines the 2's complement. We call it 2's complementer. If the opcode is addition, in that case, that whatever is operand 2 comes directly through it. But if opcode is subtraction, then 2's complement is found here, and then addition is done. Operation that is needed is only addition. Okay. Therefore, this is the second advantage of having a 2's complement representation, and that is why the integers in computers are generally represented in 2's complement form when we take both positive and negative integers. Now let us see, if we have 4-bit number, this is the, as I said, this maximum number I can go up to +7, and the minimum is -8. Maximum is 2 to the power n minus 1 minus 1, and the minimum number that you can represent is -2 to the power n minus 1. So if we have a 16-bit number, which is in fact our integer in C, then we can go up to 2 to the power 15 minus 1, or the maximum positive number, which is our +32767. This is in the case of an integer 16-bit representation. And in the negative side, we can go up to 2 to the power minus 2 to the power 15, which is our number is -32768. This is a range that we can represent. One important thing that we should see, that say for example a positive number 4, okay, so 0 1 0 0. If we take say +4 0 1 0 0, okay, which is +4, and instead of 4-bit, if you want to represent it as an 8-bit, you see what we'll have to simply do is to duplicate the sign bit towards the left. For example, if we have say +4, then we get 0 0 0 0, okay, then 0 1 0 0 as +4 in the 8-bit representation. Now see, what is your, if you have a -4, in that case I have 1 1 0 0, therefore 1 1 0 0 is -4 in 2's complement representation. And if we have to represent -4 in 8-bit, here also we simply propagate the sign bit towards the left. For example, this will be represented say 1 1 0 0, and you propagate the sign bit towards the left, which is your -4 in 8-bit. Okay, so this was our 8-bit. This is our 4-bit representation. Now let's, why I say this is this, the following reason. Say in the case of an integer, generally you have 16 bits, and therefore this is the two ranges that you can represent. Okay. Say if we have a long integer, as we know that long integer generally is 64-bit, then we have oh sorry, long integer is 32-bit. In that case, say 32-bit integer, we have 2 to the power 31 minus 1 is the maximum number that we can go, and this is plus 2 1 4 7 4 8 3 6 4 7 on the positive side, and minus 2 to the power 31, which is minus 2 1 4 7 4 8 3 6 4 7 is a maximum negative number that I can represent. Therefore, this is the highest number that I can represent in integer. This is the lowest number that I can represent in integer with a unique 0. Now, when we convert a 16-bit number to a 32-bit number, what we'll have to simply do is this: propagate the sign bit towards the left to fill up the rest of the positions, that as we have done to convert a 4-bit number into an 8-bit number. That is what the computer does to fit a 16-bit number into a 32-bit number. Okay, that is so far as our addition and subtraction is concerned. Let us see that if we have to do multiplication, then how the computer does the operation. Let us take the case of a sign magnitude representation first. Okay, and let's take the case of a decimal number system. Okay, say we have a number which is minus 32, and we want to multiply plus 23. Okay, operation that we want to do is addition, multiplication. Then let us see what the way we go. We first take this. It's a basic paper and pencil method that we employ here. We get 6 and then 9, and then shift this partial product towards right. Then we get 4 here, 6 here, right? We then get 6, 3, 7. Now, after doing this operation, when we do this operation, we do not take the sign into consideration. We just forget about the sign, and after the operation is over, we see that what sign bits were there to decide that what would be the sign bit over to here. If both of them are negative or both of them are positive, then sign turns out to be positive, otherwise the sign turns out to be negative. Now, similarly, in the case of a binary, the same paper and pencil method we can employ. Say, for example, we want to multiply minus 6 with, say, plus 5. Okay. What we are trying to do is that binary multiplication. Now, minus 6 will be represented in a sign magnitude form as 1, 1, 1, 0, okay, and plus 5 will be 0, 1, 0, 1. Okay. Now, in the sign magnitude form, as was we did in the binary representation, let us first forget about the sign. Let us take 6 and 5 as unsigned to unsigned numbers, okay, and then start the multiplication. First, it will be 1, 1, 0, since this bit is 1. Okay, this is our partial product. Then we give the partial product a right shape. Then since this bit is 0 now, we get 0, 0, 0, add them, okay, we get 0, 1, 1, 0. This is the next partial product. We give a right shift to the entire thing, okay, and this is 1, therefore we have 1, 1, 0, Therefore, if we add them, we get 0, 1, 1, 1, 1, okay, which is 30 in the unsigned form, okay. Now, we can decide about that since this is one is positive number, another is negative number. Therefore, the sign should be negative, and therefore we can put a sign bit over to here to say that this is a negative number. Now, let's see that what are the basic hardware that is needed to do multiplication in this way. That means in addition and shifting, that is the two operations that we need. We are talking right now of multiplication in the sign magnitude representation. Now, in the sign magnitude representation, we are forgetting the sign, doing the multiplication on these two unsigned portion, and then decide about the sign. Now, the hardware that is needed, therefore, is basically that you need addition operation to be done and a shifting operation to be done as we have done over to here. The basic hardware can be thought of like this, that you have a multiplicand register where you can put the n bit multiplicand m0 to mn minus 1 bits. You have a multiplier register. This is our multiplier register. This is also an n bit register. This is what we can call an accumulator, an auxiliary register that we keep here. That is also an n bit register. Here, this is an basically adder, okay, and the result that we have here, that is this n bit and this n bit, I can shift to the right. That means this goes to the right, this goes to the right, and when I am doing addition, if there is some carry that is generated out of the most significant bit, that the carry comes over to here. We have here an adder and shift control unit, that is this unit, which adds, which decides that when the add operation will be done, and which also decides that whether the content of this A register and this Q register will be shifted towards the right, or as has been shown in the green color, whether shifted to the left or not. That means that the entire A register and Q register can be shifted one bit to the right. The entire A and Q register can be shifted one bit to the left. Whatever carry that is generated, by carry I mean that is generated out of the most significant bit of the numbers, that can come over to here, and if it is needed, that carry can enter into the A register. Similarly, we keep another register here, we call it Q minus 1 bit register, where whatever comes out of Q0, if necessary, it can be held over here. Now, this is the addition operation is done this way, that this comes here, then whatever is generated here, the partial sum, we call the partial product, okay, can be come back once more as operand 1, and the addition can be done. And once the addition is done, the shifting can be done. The shifting can be done, as I said, on the right direction or on the left direction. In the case of an multiplication, what we'll need is the shifting is to be done towards the right. Okay, why this general system has been kept so that it can be shifted towards the right or towards the left? Because we will be needing shifting towards the left when we do the division with the same circuitry. But let's forget the division right now. Let us do the addition with this simple circuit. Say, let's take two numbers, 6 and 5, unsigned, right? we have kept M, the multiplicand 6 we have kept here 1 1 0. A register initially has been cleared, that means this A register has been cleared. Okay. Q register 101 has been kept. Okay. And since we are talking about 3-bit unsigned numbers, the count has been kept as 3. Okay. Therefore, count has been loaded with 3. Okay. This is the initialization. Multiplicand has been loaded here. A multiplier has been loaded here. A register has been cleared out. The entire circuitry has been arranged that shifting right will take place. Okay. And the operation is allowed to go. Now, since Q0 is 1 here, therefore we add the multiplicand with A, okay, to get 1 1 0. And after we get it, then we make a shift right. This 1 comes here, this 1 comes here, this 0 comes here, and so on. Make a shift right, and the count is reduced. Now, the Q0 is 0, and therefore no addition is needed. We simply shift. Okay, therefore this 0 comes here, this 1 comes here, this 1 comes here, and so on. Whatever comes out of the least significant bit of Q0 is ignored. Now we find once more here that Q0 equal to 1, and therefore addition is done. And when we add, say 1 1 0 with 0 0 1, we get 1 1 1 here. Okay. And then we shift. That means we give a right shift to the thing. 1 comes here, 1 comes here, 1 comes here, and so on. Count turns out to be 0, and as soon as the count turns out to be 0, we stop. And this is the result. And you can see that we have got 30 as the result. Okay, this is our result. And you see that the simple operations can be done by means of this circuit, as has been explained. The add and shift control is done by this control circuitry. Now, this is so far as our sign magnitude representation is concerned. Okay, but what about the 2's complement representation? Because sign magnitude representation, as I said, that is very rarely used. The 2's complement representation is used. Okay, and therefore let us see the sign and the 2's complement representation multiplication. Achha, one thing that I should say, that when talking about this sign magnitude representation multiplication, basically we have stripped the sign bit. We have to add the sign bit after the operation is concerned. The operation is done on unsigned numbers. Okay. Now let us see that 2's complement representation, the algorithm for it. The algorithm for the 2's complement representation, one famous algorithm is Booth's algorithm, that is very much in use, and the algorithm in the form of a flowchart has been shown over here. Okay. Once more, say that we use the same basic hardware. The initialization that we do once more is that A register is cleared, Q minus 1 register is used in this case. Okay, Q minus 1 register is used, and that Q minus 1 register is initialized to 0. Okay, then M multiplicand is put into the M register. The multiplier once more is put into the Q register, and the count is set to N. That means the size of the number. Okay. Now, what is done is that the Q0, Q minus 1, these 2 bits, that means this bit and this bit, which is initialized to 0, is tested simultaneously. Okay. Both the bits. In the previous case, we are testing only this bit. If we find that this 2 bit is 0 1, then we add M to A and put the result into A. If we find that these 2 bits are 1 0, then M is subtracted from A and the result is put to A. And if you find that these 2 bits are either 0 0 or 1 1, then we do neither addition nor subtraction. We come straight over to here. We make an arithmetic shift right of a, q and q minus 1. That means this a, q and q minus 1 is given an arithmetic shift right. By arithmetic shift right, we mean that whatever is the sign bit here is replicated. This C bit is not entered into this A register or the accumulator. Okay, whatever be the sign bit, that is replicated. We make an arithmetic shift right and reduce the count. If we found that the count is non-zero, then we repeat this process. If we find that the count is equal to 0, then we stop to get the result. Okay, this is the Booth's algorithm. Let us take an example and see that how does it work. Let us say that we are talking about 4 bits. We are trying to multiply -7 with 3. Okay. The M register has been loaded with -7, which is this value 1001 in 2's complement form. Then the Q register is loaded with 30011. Okay, and the A register is cleared out. Q minus 1 has been initialized to 0. Therefore, you see that, let us go step by step. Okay, this part is our initialization. Okay, now we test the Q0 and Q minus 1 bit. Since this is 1 0, we perform A minus M going to A, which means we perform A minus M, we take 0 0 0 0, that means, and minus M will be, let's find the 2's complement of this, that means it will be 0 1 1 1, 2's complement of this, and we add, that means we get 0 1 1 1, which we get over here. Okay, therefore A minus M is put into A here. Okay, and after doing that, we shift and reduce a count. Shifting, you see that 0 comes here, that 1 comes here, and so on. The entire thing shifted out. This one comes over to here. This is an arithmetic shift, which means you see the sign bit has been replicated here. Now, as I have said already, that if I propagate the sign bit towards the left, the representation of the number doesn't change. That means the number remains the same. For example, if it's a negative number, say 1101, which is -5, and if I go on propagating the sign bit towards left, then it remains -5. That is why we replicate the sign bit. Okay, and this shift is called the arithmetic shift right. Now, similarly, you see now, since Q0, Q minus 1 is 1 1, okay, we don't do any operation, we simply shift. Okay, therefore, this is shifted here. Okay, Q0, Q minus 1 is 1 1, Q0, Q minus 1 is 1 1, therefore, the shifting is done. This comes here, and so on. Okay, therefore, the entire thing is shifted right. Then next we see Q0, Q minus 1, Q0, Q minus 1 is 0 1, Q0, this is Q0, this is Q0, Q minus 1, this is 0 1, therefore, we add. What we take this one, add with this one to get this result. Okay, M plus A, whatever is the content of A, okay, these two are added and we get this one, right? And then once more we shift right, reduce the count. Therefore, this comes here, and shift count is reduced to 1. And we now find that you see that the Q minus 1 and Q bit is now 0 0. That means this is 0, this is 0, and therefore we'll have to shift only. Therefore, this comes here, this comes here, and so on, and the sign bit is replicated. And you see, if we do it this way, that n now turns out to be 0 and the operation is stopped. The entire thing, whatever is contained now in A and Q register, okay, the entire thing now represents the results. I'm sorry, up to this Q minus 1 is not taken into consideration of the result. Therefore, this is a result which, if you find that this is minus 21 in 2's complement representation. Okay. Therefore, what I suggest is that you take the Booth's algorithm, okay, take these two numbers, any two number, and go through this Booth's algorithm, okay, to do the operation. You will find that the result will be left in the A and Q register taken together as the representation of the number, either positive or negative, in 2's complement form. Okay, that is our Booth's algorithm, and the simple circuit that we use to do this is this, which I say will be used for division also, which I will be discussing in the next class.